All right, so let me thank the organizers first for giving me the chance to speak. And we have a youngest applied topologist here, so I have a great pressure on me to inspire him. Okay, so I'll be talking about quasi zigzag persistence. This is a technique we found that it is useful for time varying data. So 2 years back, and this is a joint work with 3 of my students. Actually, 2 of them have already graduated. This project started 2 years back, more than 2 years back, where we wanted to study multiparameter persistence for analyzing data, particularly through the machine learning pipeline. And that project we call GREEN, the acronym for Generalized Rank Invariant Landscape. So, and that project we finished, we wrote a paper, and then that led to this project, the Quasi Zigzag Persistence. Basically, Quasi Zigzag Persistence combine multiparameter persistence, particularly 2-parameter persistence, with the zigzag. I have been working on zigzag quite a bit last few years, and suddenly we find that zigzag and multiparameter together becomes quite useful for analyzing time varying data, and that's what I'm going to say. But before coming to the quasi zigzag persistence, I'll introduce you to first the GREEN. So I don't have to say much about this to this audience, so let me skip this. Okay, so one of the main goals in data analysis through machine learning is to like if we are using barcodes for it, vectorization of the barcode, because this pipeline works on vectors. So how do you vectorize the barcodes? There have been quite a few techniques have been proposed already. So one goes to Peter, the persistent landscape, which is very well known now. And then there are persistent image, sliced Wasserstein's kernel, rational hat, Pursley, and maybe there are a few more, which please pardon me if I missed your favorite technique. So this has been done, and before, but mostly these were used for 1-parameter case. So here we are going to do the 2-parameter case, but before I go to the 2-parameter persistence, I'll just assume that most of you know about 2-parameter persistence, but let me introduce what my assumptions are. So this 2-parameter persistence I'm assuming is induced by filtration. So xij's or x alpha betas are some spaces filtered by these 2 parameters, alphas and betas, and they're related by inclusion. That's why I'm calling them as a filtration. This is a generalization of the filtration in 1-parameter case. So instead of 1 axis, now you have 2 axes. But if you look into it, it goes in the x direction monotonically, y direction also monotonically. The complex or the spaces grows because of the inclusion. So you can replace this x as simplicial complexes, for example. For this talk, I assume everything finite. So no pathological cases, because that makes my life easier and my talk also easier. These are simplicial complexes indexed by 2 parameters here. So we know that once I have this, then if we put the homology functor, basically take the homology groups of simplicial homology of all these simplicial complexes, then the inclusion are replaced by the linear maps. And if the homology groups are taken with a field coefficient, finite field coefficient, I'll be assuming mostly Z2. So in that case, what you get such a diagram that every point, grid point, you have a vector space, and between the vector spaces, there are linear maps induced by inclusions. So that's the algebraic structure we have. Okay, so just to be a little bit familiar with what happens from the by filtration to the algebraic structure called the persistent module. Here is a very toy example. So suppose I have this simplicial complex There are two vertices, V1 and V2, and the edge E, and these are the grades, or basically these are the grid points where they come in first time. So for example, V1 comes in here, 0, 1, V2 comes in 1, 0, and E comes at here at 2, 2 grade. Okay, if you have, so this is a filtration, bifiltration. Okay, because if this one is coming, it is available everywhere in the upset. V1 is coming, it is available in the upset, and E is available in the upper corner. Okay, but if you have such a bifiltration, and if you consider the homology groups, say let's take A0 here, the zeroth homology group, the number of components, what you get, the picture, a visualization of the persistent module will be something like this. Like there is a component which starts at V1 and it is available in this upset. V2 is another one, it is also available in this upset. And this region here, the purple region, there are two components. So here there is only one component, in this region one component, but here, because they both come in and give you two components. But then something happens here, when the edge E comes in, you have a relation. Basically two components become one component dies, and I'm denoting it as V1 plus V2 becomes 0. So it's a relation which is created or coming in at the grade 1, 1. So the structure, if you think about it, there are like a sheet going upward from V1, another one V2. These are the two generators generating this modules, and then these two are joining here at this point and also along these edges. So that's the structure. This is a very simple bifiltration, but you get a persistent module which is not that simple. It's not a very straightforward persistent module. It is indecomposable. You cannot make it any simpler. And this indecomposable, this is not an interval also, because things are joining together. And that's a very typical phenomenon which happens in two-parameter case. This phenomenon does not happen generally in one-parameter case, because you can always have the decomposition where every indecomposable are intervals. But that's not true for two-parameter case or beyond. Okay. So two-parameter also, since we have the two-parameter persistence, we also have the problem of vectorization to apply it to neural network framework or machine learning framework. And again, we are not the first one. Many of the work have already been proposed to do that. And Hypon actually generalized this landscape concept to the two-parameter, multiparameter case. And then there are others also, multiparameter persistent images, multiparameter persistent kernel, and latest one, graph code by Kerber and Dussault. Actually, this year they have. So there have been quite a few ones which are proposed, and we are proposing another one here. And of course, I'm not going to compare who is better, who is not, because I believe there are always a data set for which yours is better, and others are not, and showing that one doesn't make much sense. Okay, so let me introduce what we mean by GRIL. GRIL is generalized rank invariant landscape. Okay, so the definition is, so for me, I'm assuming that M is a persistent module indexed by a poset P is finite, and so basically every point in the poset has a vector space, and I'm assuming vec is the category of finite dimensional vector spaces. So this is so M can be thought of as a functor going from the poset category to the vec category. So that's the way, the functorial view of the persistent module. That's what I will take it here. And then suppose that I assume also P to be connected. Connected means any two points in the poset are connected by other points which who are comparable, or basically there is a path between any two points through the other points of the poset who are comparable. Okay, so connected poset, and I assume, suppose there is a sub-poset I of this connected poset. Generally I will take it as an interval. So interval, remember there are two major conditions that an interval has to satisfy. First, it has to be connected. Second, it has to be convex with respect to the relation. If 2 points A and B are there, and any point in between A and B with respect to the relation has to be there. So that's the definition of the intervals. Okay, so one of the definition which we will be working on called the generalized rank. So we are familiar with ranks. So basically, even in one parameter case, if you take 2 points and the map from the left point to the right point, you take the vector space and the linear map and take the rank of this map, and that's the rank invariant. You do it for every pair. Okay, but here what we are going to do, we are going to generalize this concept, because in 2 parameter case, think about it, the intervals are not like very simple thing, because the interval could be a little bit more complicated. I'll show you some pictures, and there you don't have a notion of rank. Only the rank is valid if your interval is like a rectangle. Then from the bottom left corner to the right upper corner, there is a notion of rank over the diagonal. But if the interval is more complicated, then the rank concept does not work. So that's why this concept of generalized rank came in. This definition is due to Kim and Memoli. And what does it say? The rank, which I am denoting as rank of M on the support of I, is given by the rank of the limit to co-limit map. I hope you will know what is the limit and what is a co-limit for a diagram, and so that's what I'm doing here. But I'm taking the limit of M restricted to I. That's why I'm denoting that always I is a subset of M. So I'm defining the rank of M over I as the rank of the limit to co-limit. Okay, so what does it mean? Okay, so if I is a rectangle, this definition actually gives you the usual rank. If I is a rectangle, this definition limit to co-limit rank is exactly what we know as the rank over the diagonal. The other property is that this rank function actually is monotone, in the sense that if J is an interval included in the interval I, then rank of I is less than equal to rank of J. Okay, so basically, as you are expanding the interval, the rank cannot be increasing. That's what it says. It has to either stay same or decrease. Okay, so what do we mean by this generalized rank? So basically, generalized rank means over the interval I, how many topological features are surviving over the entire interval. That's the meaning of the generalized rank. So for example, if I take such a bifiltration, like I'm showing it here, these are the vertices, edges, only up to edges I'm bringing them in, and these are the inclusion arrows, and corresponding to this, here I'm drawing the algebraic structure. And you can see, if I take the interval as this, for example, this segment here, then the rank is nothing but it will be 3, the number, because there are 3 features which are surviving. And if I take this one as my interval, I think there will be 2. And if you take the entire one, the rank will be only 1, because only 1 survives over the entire square. Okay, that's what the meaning of, intuitively that's the meaning of the rank. Okay, so now let me define something what we call worms. What is a worm? So first, a P-centered delta square is basically a square centered at the point P with the side length delta. Okay, and worm is the union of 3 such squares. So here I am showing, like you take this square, delta square, and union with 2 more in the anti-diagonal positions. Their centers at one is here, another is here, and this is exactly the definition. If you take the union, we get what we are calling as the worm, P delta 2. Actually, you could have generalized it for any number. That's why the name came. It looks like a worm. That's why we chose the name 1. Okay. So now, what is the definition of grill? The grill is a function which I am denoted as lambda m, which takes two parameters, a point p on your poset p, and a value k, an integer k. Okay, and basically this definition, what it is saying is that how much can I go on expanding the original one such that the generalized rank over this new expanded interval still remain greater than equal to k, and you cannot increase it any further, because if you increase it any further, it will drop down below. And that's the width of, so basically the width of the expanded one is the value at the point P, the grill value. Okay, so at this point P, I'll get the value, what is the, for example, suppose in this case I can expand this one up to this one, and the width of this expanded one will be the value at P, because if I try to increase it any further, probably in this case, the rank drops down below. Okay, so that's the definition of the grill at a particular point P, the value. Yeah.
So any other reason why you do it on the multiparameter one
instead of? Yeah, you could have taken the other way also, but we just chose this way. All right. So let me tell you a little bit in concrete terms what this grill value is doing on this particular example. Remember, I took this example, the same example. I started with this two parameter. From this bifiltration, we get the two parameter persistent module. In this case, suppose we have center points at P1, P2, say P3 up to say K points. So for every point Pi, I'll get a grill value. So I'll get a vector. So this is the vector in the horizontal direction for K is equal to 1. I can take K is equal to 1, K is equal to 2, whatever you fix the K, then for a particular fixed K, you get a vector which is giving the values at different chosen center points Pi's. Okay, so in this case, let me say, so this is a concrete example. At this point P1, if I put K is equal to 1, I can expand this one only up to this pink one, because if you expand it beyond this, then the rank should drop down below 1. Why is that so? Okay, so 2, I'm not. Okay, so why in this case it is dropping down? Let me see. Oh, maybe this is 1. Oh, generalized rank. Yeah, so in this case the generalized rank will drop down below 1 if I try to expand it any further. But for example, this green one in P2, I cannot expand it any further because green one is centered somewhere here. If I go past this edge, it will be 1, 0. Okay, that's why this is the one you will have a value, whatever width you have, you will have a value here. Whatever width of this pink one, you will have a value here. So that's the way you get a vector for the persistent module A with the chosen center points. And that's the vector I'll be using as the grill feature to use for the neural network framework, the vectorization. Okay, and for chosen different values of K, you will get different values. Okay, so let me see. So what we could prove that this grill is stable with respect to the input by filtration function that is given f and g, which is defining this input by filtration, and corresponding to this input by filtration, suppose you have the persistent module mf and mg, and take the grill vector lambda mf and lambda mg, then their difference in the L infinity norm is bounded from above between the two function values in L infinity norm. So this is typical stability property. So it means that real values are stable is useful. So in practice. Okay. Let me skip this picture. Okay. So now how do we compute the generalized rank? So the crux of this definition is that given an interval, I have to compute the generalized rank over this interval. How would you do this? And here comes one of our main results in 2022 with Kim and Memoli and myself. We gave an algorithm how to compute the generalized rank and use zigzag. And it turns out to be really simple actually, that you can compute the generalized rank at least in 2-parameter case with this result very simply. Okay. So let me define what does it mean. So suppose this is a typical interval I in 2-parameter case, and then I'm going to define what is a boundary cap of this interval. Boundary cap basically is you take the minima of the coset. In this case there are 3 minima, particularly with respect to this interval, and there are maxima, 3 maxima. Join them with a minimal path on the boundary, like here the green path, here is the purple path, and then join these 2 endpoints with this upper leftmost point. So that gives you a path up to this, which we are calling as the boundary cap. It's like a boundary of the interval is capping from the top. I could have taken actually that, not cap, from the bottom also, but we chose the term cap, that's why we are doing it from the above, okay? It doesn't matter how you choose this path. But the result says the following. The result says that the generalized rank of this interval is given by, if you take the zigzag, remember, if I go over this path, this becomes a zigzag path in the sense I go here, and then this direction is the opposite of the inclusion. So I get up, inclusion, in this case opposite of the inclusion, because this direction are all the inclusion. Then again here zigzag, then you go up, go here on the right hand side, here also you zigzag. So you ultimately get corresponding to the given filtration on this boundary. If you restrict the filtration, you get a zigzag filtration. Okay, so now once you have this zigzag filtration, you have a zigzag persistent module induced by zigzag filtration. Now you compute the barcode of this zigzag persistent module, the interval decomposition, and look at how many bars are full, in the sense it starts from the beginning, it goes all the way to the end. The number of such full intervals in the decomposition is exactly equal to the generalized rank, which is over this 2-dimensional domain. So suddenly from a 2-dimension, I can go to a 1-dimensional case, and we know how to compute decomposition of the zigzag persistent module. In fact, we have a very good algorithm now, that is because I have worked out with one of my students, Tao, which makes zigzag computation very simple now and very fast. So we applied that now to compute the generalized rank of the intervals. Okay, so that's the way you can compute the. So here what I was saying. Actually, this has been implemented. The zigzag persistent module is available. The code is available. You can try. Okay. Okay. So now here I'm just giving you the algorithm. Algorithm is quite simple. From the point, any chosen point P, you start with a small interval, and you can, to determine what is the real value at the point P, you can do a binary search over the width of the interval. Okay, so that you don't it saves you time. You get a log behavior rather than linear behavior. And you can do it because the real value is monotone with respect to the width. Okay, so you can do a binary search, which is very useful actually in practice to make it efficient algorithm. Okay, so we did this is the drill, and we applied on several data sets. Those of you who have worked on neural network or these are well-known benchmark data set, proteins, DHFR, IMDb binary, COX2 mutat. These are well-known benchmark data sets. And these are graph data sets, and we wanted to do the classification of these graphs because many papers use them, and so we can compare our results with theirs. So that's why we chose it, and we applied it. And this one was a binary classification task. So of course, for the graphs, think about it. These are the graph data sets. I need two values because this is two parameter. What we chose, hit kernel signature and Ricci curvature. These are the ones which have been chosen by others also, I think. That's why we also chose that, so that we can compare our results with theirs. And we computed the real values for k is equal to 1, 2, 3, 4, 5. These 5 values. And so the question is, how do you choose point P? P could be chosen every grid point, but that will be too much. So suppose, for example, if I have 50 by 50 grids, then computing this generalized rank for every centering at every point will be too much. So instead, we just sample certain points uniformly so that it becomes useful. At the same time, computation is not too much. And here are the results. So the way it is, so these NP1, NPK, NPL, these are the multiparameter based classification algorithms by others. Okay, these are the 3, and we are comparing it with our grid. And whenever you see red, means that is the best. And the blue, yes, that is the best, and blue is the second best. And green is doing a good job, but again, I cannot claim that it does all the time the best one. And sometimes it's, well, again, as I said, green will do very well if the graphs has more cycles, because then because we are using H1 and H0. So if the graphs do not have that much of cycles, if it is mostly tree-like, then H1 is almost 0, and it has less discriminating power than the graphs which have more cycles. So this is one of the reasons sometimes it does not do well, but most of the time, but it is comparable. You can see, and many of the times actually it gives a better results. Okay, and let me see, what is this? So we use this 50 by 50 grid, and here what we did is, I think the best use of grid not by itself, but use it in conjunction with somebody else which have proven to be good. So for example, already we have GCN and GIN, for example, these are the models. These are the architectures already well known to perform well for the graphs. What we did, we augmented the features with the grid features. And then we see what it is doing on these data sets. And again, you can see that whenever you put grid on top of these well-known networks, it does gives better results. Okay, and remember this GIN, GCN, they have been like really fine-tuned to work very well for the graphs, and they have so many parameters and blah blah blah, all those things. Our method does not have any hyperparameter tuning. We did not do anything. It's just grid features. And remember, grid features, there are hardly any parameter, one or a couple of parameters. So that is one of the things which are hidden, but that's the benefit of most of the topological data analysis probably compared to well-known all these network things, because you don't know how many parameters they are using. Okay. Now I come to the ZZ grill. So grill, and then we are doing the zigzag with the grill, which we are calling ZZ grill. Okay. Let's see. And this is going to be used for time varying data. So time varying data, and this technique, the one I am going to propose, is very general. It's not only for time series data. It could be point cloud moving, that also the same technique will apply. So this is a cartoon picture, or a graph, or a network, changing network. Like edges are coming in, edges are deleted, vertices are coming in, vertices deleted, those kinds of moving data, moving graph, changing graph, moving point cloud, or time series data, this can be used. Okay, so here I am showing some of the example datasets. For example, this one is the ECG. Okay, here ECG of MI patient. MI is the myocardiac infarction. Basically, the patients have cardiac arrest. And what are these time series? Different time series are given by the ECG with different leads. So instead of only one lead, you get only one, but you get with different leads, you get different time series data. And that's sometimes called multivariate time series data, like this one. And this is the healthy control. Healthy patient is not patient. Healthy person should look like this, and the person who has a cardiac arrest will look like this. So can we classify between these two? So that was the task. We applied it. We did not apply on this one, but on some other time series data set multivariate we applied. And or it could be like something like this, like different types of hand movements. Like this is like drawing a tick, and this is like tennis serve. So once you get this series of images, can you classify that this image is basically serving tennis, the other one is drawing a tick? And we apply to this kind of data. And here is a network evolution, like the graph, the network, social network, for example, keeps on changing. And again, remember, zigzag is useful because ordinary persistence only allow insertions. And I said in my workshop talk also, zigzag is very powerful because it allows deletions. So those of us who come from computer science will always recognize that deletions most of the time in many problems are always harder. Insertions are easier. Those of you who know Delaunay triangulation, inserting a new point in Delaunay triangulation is much easier than deleting a point and maintaining Delaunay triangulation. That's a very general phenomenon. And zigzag is allowing the deletions. Okay, so now let's look into this point cloud thing. It's a very cartoon picture again. So I have a point cloud which is moving like these 3 points, which are changing their position. And in this axis, I put a threshold of Reeves filtration threshold delta. Like whenever 2 points come less than equal to delta distance, I put an edge. Okay, and delta is increasing in this direction. And now we can see this direction sometimes may not give you always monotonous direction. Like here, this inclusion is this way and this inclusion is this way, that is a zigzag here. So exactly for the moving point cloud, you have this situation. On this horizontal axis, it can be zigzag with respect to the complex inclusions. Although on the vertical axis, you have always inclusion in the same direction. And such a type of, so this gives you, this kind of filtration gives you a persistent module where the arrows are monotone only in the vertical direction, but along the horizontal direction, it can zigzag. And that's why I'm calling it as quasi zigzag persistence, because this is not a 2-parameter persistent, that both axes it is going in the increasing direction, but in one axis it can be zigzag, other axis is non-zigzag. So that's why I'm calling it as quasi zigzag. And this is very natural. It comes in the point cloud, moving point cloud. It comes also changing graphs, and I'll show you even you can apply it for the time series data. Okay, so now the pipeline still works. I can still define and worm and interval and all those things. But let me go over it a little bit. So here now, my assumption is that this direction it will be zigzag. Inclusion flips. Although in this direction is moving. Okay, and you get still a persistent module by applying the homology group, and inclusion also gives a linear map. Everything is so far so good. Very simple. And then one has to define what we mean by this quasi zigzag poset. So quasi zigzag poset is the subposet of the ZZ is the zigzag poset in the horizontal direction, and quasi zigzag poset is basically subposet of this product. Z is vertical direction, horizontal direction is zigzag, ZZ. You can define the ZZ and Z very formally. I am not going to do it here, it's in the paper. But once you have this quasi zigzag poset, you can still define the persistent module as a functor from this poset, as I have done it, and I'll call it a QZ module. Okay, so now we define the ZZ grill exactly the same way as we define the grill. Okay, so there is hardly any difference. Okay, centering a point, you define the generalized rank again with centering the point P with a value K is the supremum of the expansion such that the rank drops down below K. That's the definition. So definition goes through. Okay, the original definition. So this is still I can now define ZZ grill value for this particular case. Okay, so now the theorem of stability. So stability luckily we could prove the stability. Only thing is this stability proof is a little bit more technical because we use the concept of this is something called the erosion distance, which was introduced by Patel and Kim and Memoli later. So, and we proved that this difference between the ZZ grill value is exactly equal to the erosion distance, and this is bounded from above by the interleaving distance between the two modules. Of course, you can ask how do you define interleaving distance between zigzag modules? Of course, but then you can use the technique of Lesnick and Botman. I think 2012 or 13, I forget. 2008 maybe later, 2018 paper, they showed that you can lift a zigzag module to a 2-parameter module, and using the interleaving distance between the 2-parameter persistent module, you can define an interleaving distance for the zigzag persistent module. So now we can use the same technique. Only thing now I have 2 parameters already there. Previously you had the zigzag module only 1 parameter and you lifted it to 2 parameter, but now we have to lift it from the 2 to 3 parameter. Okay, but you can do it. You can do all these things, technical thing, and still define what is an interleaving distance. It's in the paper, and you can prove that this is bounded from above by the interleaving distance. So stability is still there. Okay. Okay, so now, how do we compute the ZZ grill now? Remember, I have to compute the generalized rank over an interval. But now the interval definition has to satisfy the order by which I have defined this ZZ subposet of ZZ cross Z. And it can be that an interval in this quasi-zigzag poset may not be the interval in the Z2 poset. Remember, as a point set, they are same. All points in the ZZ quasi-zigzag poset are also Z2 points. So, only thing order I have changed, the relation I have changed. Okay, and it turns out that an interval in Z2 poset may not be an interval in the ZZ poset, and vice versa. Okay, so I have to take care of this definition of interval and boundary cap and all those things. But luckily you could do this. It's not that difficult. What we are going to do? So as a result, I cannot apply our own results to compute the ZZ grill using the boundary cap, because that result really used the fact that it was coming from the 2-parameter persistent, from a Z2 poset. Okay, but this is not. So I cannot just blindly apply it and expect that this will work. It worked, but it needed a proof. And somehow it needed a proof, and we were lucky to extract such results from the category theory. And there was some results by Real in the book, chapter 8. And we used that particular result, which are called initial functor and terminal functor. Using that concept, we could still prove that this result holds. that the generalized rank on such an interval, which I should not call an interval, but I am calling an interval in this QZ poset as an interval if it is an interval in the Z2 ordering. Like here, this is not an interval in the quasi-zigzag poset, but it is an interval if I use the Z2 ordering. So I'm calling an interval in the QZ poset if it is already an interval in the Z2 ordering, like here. And then you can define actually boundary. You can define the boundary cap again. But look at it. Look at this. It's a very curious. Like this is not a minimum at all anymore. Because why? Because this way it goes. Let me see. How is it going? Oh, okay. So this direction actually is given by this arrow. So the arrow is coming this way and this is going this way. So this is not a minimum at all. Although it is a minimum in the Z2 ordering. Okay. The minimum in this case are only this, this, and this, and the maximum are only this and this. This will not be maximum in the Z2 ordering, but here it is maximum because the two arrows are coming to this point. But still, using this concept of boundary cap borrowed from the Z2 poset, I can still define a boundary cap on quasi-zigzag poset interval, and then apply the results that still the generalized rank is given by the number of full modules in the zigzag module restricted to the boundary cap. Okay, what did we need? We needed this, to prove this, we needed this concept of initial functors. What is the initial functor? A subposet, I'm simplifying things here a lot. Those of you who know category theory, probably there are more, actually there are much deeper results and much deeper concepts, but I'm simplifying things here. A subposet P prime of P is called initial if for every point P which is not in P prime, the downset of P intersect P prime in one single component. Then we call it initial. The P prime is initial. So let's see. In this case, it turns out this green subposet, this will be an initial. Okay? Alright, and similarly you define what is a terminal using the upset. For the initial, I use the downset for the point P. If you take the upset, you get what is a terminal subposet. So in this case, the terminal subposet will be this upper part, this part. Okay, so once you have that, then you can also define for the interval I, the lower fence, which I am calling as partial Li, upper fence, which I am calling as a partial Ui, and of course partial I, which is the entire boundary. Okay, and then the functors, which I am calling as f of L, which basically includes the lower fence into the I, the full interval. That functor is initial because its domain is initial. One is to prove that this lower fence is initial according to this definition. But we could prove it. Or the upper fence is terminal according to the definition. Once you have that, then we have these two functors, one by inclusion, one by projection. You get initial functor and terminal functors. And the result on this is what chapter 8 of Real 14. Actually, I was alerted to this result by Michael Lesnick. I owe to him a lot. I didn't know about this result, and we are thinking of proving it from scratch, and it turns out to be very difficult to prove. At least we could not give a very simple proof. But then once I see this, that this result exists, you can see immediately that things work. Okay, and then this result says that the proposition says once you have an initial, so basically if you have the limit of m and the limit of m restricted to the lower fence, there is an isomorphism from this limit to this limit. Similarly, there is an isomorphism from the co-limit to the co-limit here. Okay, so this is saying that I can concentrate only on the lower fence or the upper fence. I can forget about I inside, just like in the Z2 case. So this proposition ultimately helped us to prove that ultimately this result is valid, that whatever I had is still valid. So it turns out that, at least for the proof, that this is really a quasi-zigzag poset, that one direction is monotone, other direction is zigzag. If, for example, it turned out to be that a point in the middle of the interval is a minimum or maximum, things will go bad. It will be difficult to prove. Maybe it is not even correct. So in this particular situation, which is allowed by the time varying data set, we do really get this quasi-zigzag poset for which one could show these results. I do not know, maybe there are more generalization of this result, maybe it is still valid for some other types of poset, much more generalized. I have thought about it, but at least what I could see that anything inside is bad, meaning that there is a minima or maxima inside the interval, that will destroy the result. It has to be on the boundary. Okay, and since it is on the boundary, I can look only restrict to the boundaries. Okay, so here is a typical input. So for example, if I have a, like say, this is a graph, like suppose there are 3 graphs, 1, 2, 3, which are changing. How can you get from these 3 graphs this quasi-zigzag? It's a very usual standard construction. You make that, in between you put the union of the graphs, so that inclusion goes in this direction. Like this graph is included here, this graph is included because this is the union of the two. Similarly, this is the union of these two, so you get a zigzag here. So changing graph, you get a zigzag in this way, and then on this direction you can always do some standard persistence, like depending on the threshold or some weights on the edges or vertices. So this is the typical input for the graph case. You can use it. And of course, for point cloud data, I already showed you, using this threshold of the Rips parameter in one direction, the other direction automatically gives you the inclusion in the zigzag fashion because of the moving point cloud. So the changing graph and moving point cloud, you can apply the technique in a uniform, like one technique applies to both. Okay, so I copied it from the paper, and I'm not going to explain, but if you do this bifiltration very naively, it will not, well, everything is okay, it will run, but naive implementation of such a bifiltration construction is bad in practice. You have to be clever to do the bifiltration, and that's what this is what our observations are when we made this bifiltration or quasi-zigzag bifiltration very efficiently, and that's what we implemented. Okay, so I have how much? 5, 6, 7 minutes? Yeah, okay. You already took 1 minute now. Okay, so I decide now.
You have 10 minutes.
So let me give you some of the experiments. So we applied this technique for 2 types of time varying data. One is multivariate time series data. Multivariate, I already told you, is typical time series, but there are multiple time series in one data set. That's the multivariate time series data we applied. And the other is sleep stage classification. You know, during our sleep, there are several stages, like the beginning, then something called REM stage, and then awake stage, and people or the doctors want to classify for the patients these different stages. They can, like one is sleeping, or can get this time series data using some probes, and then they want to classify which stage the patient right now is in when the patient is sleeping. Okay, and there are 5 stages, and that's what I think there are 5 stages, and that's what we will do the 5-stage sleep classifications. These are very standard benchmark data for the time varying data, and I've said it. UA multivariate time series data is by these people. So yeah, and these are another data set. Let me tell you, one of the main challenges we faced to experiment is to really get data for multivariate time series data, which is on which we can experiment, on which people have experimented, because the moment you write a paper, they come back, okay, why didn't you compare this, that, and why not this data, that data, and data are always not available properly. I find it is very, what should I say, depressing to go and really do anything, because there are so much of ask for the comparisons. And often the softwares are not available. Even the software are available, they do not work. So this is a frustration a little bit. But anyway, we went ahead because we found a TDA technique for time varying data. Why not? Okay, so let me tell you how can you use it for the time series data, multivariate time series data. This is a cartoon picture. Suppose I have these 3 time series data, multivariate, that's why there are 3 time series data. And what you do, you put a window of length W, and these windows, they overlap to some extent up to the length of lambda. So what can you do for every window of W? You have sets of points, right? These values. And so you can map this entire segment to a point in RW, in W, in the dimension W. So you get a point, green point corresponding to this window. You get a green point, a blue point corresponding to this window. You get a red point corresponding to this window. That's what these 3 points are denoting. And there is a technique called Pearson correlation, and by which they can show you how these segments are correlated. So they give you a value. So depending on this value, you can draw an edge between the 2 or not. You can always put a threshold on the Pearson correlation value. Then what do you get? You exactly get, for this window there is a graph, for this window there is a graph. So it's a changing graph. Edges are appearing, disappearing, although vertices remaining the same in this case. And so you can apply the previous technique, because I already told you that it can be applied to changing graphs. Or there is an alternative also. You can treat this one as a point cloud data, because there are 3. So here there are 3 points which are living in RW, okay, and these point clouds are moving. Okay, so either you treat it as a point cloud data moving or a changing graph, and apply the same technique applies to both. Okay, and so that's the way we use on the time series data. Okay. Okay, here are some of the results. So, this is the sleep stage classification. So these are the awake, F1, N1, N2, N3. There are 3 different stages, and this is the REM stage. So there are 5 stages of the sleep, and you can apply for every stage, and you check the accuracy. And these are the well-known techniques already for the sleep stage data. But these techniques, whenever you see, they are fine-tuned so much for this particular type of data. It's very difficult to compete with them, because they have found fine-tuned it for this particular data, and here we are applying a very general technique to this data. Although still we find that it is comparable. Not only that, sometimes it improves. That means topological insights into the data does improve things. And this is what exactly we are showing, that whenever this is a very standard state-of-the-art technique, we put Zigzag drill on top of it, and it improves almost everywhere. So the moral is that don't try the topological technique by itself. Probably it will be hard to beat them, but go with them. So you put on top of them and improve, and it does improve. Okay, because these topological features most likely the other techniques did not take into account. Okay, and this is the experiment on these are the multivariate time series data. Actually, previously it was the slip stage data. This is the multivariate. So this is the finger movements, heartbeat, motor imagery, and these are different types of movements basically. And again, you apply, and there are already standard benchmark, standard methods for it. You compare, and you show that, well, many times it improves. Maybe once in a while it will miss. Okay, so it's not that all the time we improve, but many of the times it improves with the ZZ gradient. That's all. And coordinate is a very standard method, well known in this particular application. So we found coordinate, and we showed that okay, it improves. But then somebody pointed out, no, not only coordinate, there is something called tapnet. So we went there, and then we found that yes, there is a tapnet, and then again compared, we get the similar results. Okay, so basically that's it. These are more, and the method is not that computing intensive actually. It takes several hundred seconds actually. For a reasonable data set, of course, I have to say. Okay, so that's what it is. The ZZ grid, we have a software available from this website, and the paper is also on the archive. Thank you.